So thanks to the organizers for working me into the schedule in the last minute. So this has been a very interesting week. So we saw a lot of, I saw a lot of very interesting talks, a lot of very interesting ideas. And since some of us have flights, are heading to the airport fairly soon, the plan is I just want to recap some of the ideas that were discussed this week and give a way to combine them, to combine some of them to give a faster algorithm for approximate maximum undirected maximum flow. So I'll start off by describing the problem. This is the same problem that Jonah described in the previous talk, which is that I have a graph G, and I'm giving a demand B. So it's a capacitated graph with capacities C. And given this demand, I want to find a flow meeting the demands that minimizes the maximum congestion. So I want to find F meeting E and minimize max over all edges of flow on the edge divided by the capacity of that edge. So this is the undirected version. The directed version is also well studied. Aaron and Tat mentioned the latest progress, described the latest progress on this in their talk yesterday afternoon. I will be describing the approximate version of this problem, which is that if opt is the, so I will describe the 1 plus epsilon approximate version. I want this to be less or equal to 1 plus epsilon of the opt, where opt is the minimum congestion that's necessary to route a flow. Okay. So let me. So before I describe some of the, so before I describe the details of the algorithm, let me first describe the pieces that this algorithm builds upon. So in the previous talk, Jonah described a very clean way of reducing from Cut-Approximators to algorithm for approximating undirected maximum flows. So the key definition in Jonah's talk is this notion of an alpha cut-approximator. So the idea of a cut-approximator is that it's a sequence of cuts. So this will be called capital C is just a set of cuts, such that for any demand, I can approximate the minimum congestion required to route that demand by just examining all cuts in this family. So formally, what this is that for any B, opt of B is within a factor alpha of the max over all S in the cut family of the demand across it divided by the capacity across it. So this is the notion of approximation that I will use and also overload throughout this talk. It means that it's within a multiplicative factor of alpha, as in I can find lower upper bounds such that these two values are guaranteed to fall within those multiplicative lower and upper bounds. And what's happening here is that this is via something that looks like this is via a version of the maximum flow minimum cut theorem. It says that if you look at all cuts, the minimum congestion required to route the flow is given by the maximum demand across a cut. So the normalization by little c, that's just because this is the amount of capacity. So this is assuming that even if I route flow uniformly along all edges in that cut, this is the congestion that I need. And what what Jonah showed in the previous talk via an algorithm known as almost route is that suppose I have access to such an alpha cut approximator, I can quickly use it to approximately compute maximum flows. So this leads to an algorithm with O tilde alpha squared epsilon to the -2 iterations. Or 1 plus epsilon approximax flow. So I'm using the O tilde to hide factors of log n. I will do this consistently. You can track these exponents explicitly, but I just want to drop them for simplicity. And what each of these iterations consists of, it consists of measuring these prices at vertices, aggregating over cuts, and then bringing them back to vertices. So what it is that it can be viewed as a nearly linear time overhead plus time to look at all cuts. So if I have such a cut family, and with alpha that's about poly log n, this would imply nearly linear time algorithm for approximating maximum flows. So in the result by Jonah and also in the result by Kellner, Lee, Orikia, and Sidford, what the algorithm then does is that they give constructions with highly efficient constructions of alpha cut approximators whose size is also nearly linear, almost linear in size. So in the previous talk, Jonah also mentioned several other possible candidates for alpha cut approximators. And one of these was described in detail by Reiki on Monday, on the first talk this week, actually. So this is a result due to Reiki, Shah, and Tobig in Soda 14, I believe. And what they showed is that there's an algorithmic construction of these cut approximating trees. So this is that there exists a tree, so they can find such that t is within a factor of poly log of g. So here I'm starting to overload this notation of similarity. And what I'm using the similarity to denote is that I'm denoting the cut structure is more or less the same. It's worth mentioning that this tree T, in fact, actually has extra vertices in the graph as well. So it's a Steiner tree. You take the graph. What the picture looks like is that here's my graph G. They construct a hierarchical decomposition, and from this decomposition, they obtain a tree. But the good thing about this kind of tree is that it is a very succinct, very well-structured object. Trees are essentially the nicest kind of graph that we could hope for. And that it is a very good approximator of the size of all cuts.
It's a 1 or is that a pi log?
I'm using O tilde to hide log factors. So a little counterintuitively, O tilde is just a shorthand for poly log. And I know there's another convention, which is that O tilde it hides lower order terms. I guess since I already abused the notation with the approximate to be both for cuts and for scalars, I might as well abuse the notation a little further just for simplicity and hide polylog factors with these as well.
Does his original construction doesn't give you that? Doesn't his original construction give you that?
Yes.
2001?
Yes, there's a sequence of constructions by Reiki that all give you this.
Not the log n. That's why I was asking.
Because the log n one's not one tree, it's
Many.
I will come back to the distinction between these constructions in a moment. And actually, I think you've just hinted at all the overloads of notations and all the things I was hoping to sweep under the rug in this talk in one question. And you'll see what I'm going to do with this O tilde as well. the good thing about this kind of structure is that it gives a very good approximation factor, and it's efficiently evaluatable. And what that means is that we can turn it into a very good cut approximator. So the idea is that suppose I want to compute a minimum cut on a tree. And say I have a demand of -3, a demand of -1, and I have a demand of 2, a demand of 2. So one rule about routing maximum flows is that I should never route flow across an edge in both directions. This is bad because I can just cancel this unit with this unit because the flow is not splittable. Well, I'm sorry, the flow is splittable and it is the same commodity, so I never need to route from in opposite directions along the same edge. So assume I don't have this configuration. For a tree, what I have is that the amount of flow going along every edge can be uniquely defined. It's just the demand across this edge. So for example, on this edge, I know that I have a total net demand of -4 here. So I have -4. So this edge I have -4 here, and then I have 4 here. So the total amount across this edge is just 4.
You don't want to draw that at the vertex. You really mean it's for the set on the other side. Yeah. Thank you.
So I have 4 units across this edge. And also, for example, for this edge, I can look at this. I can sum the demand across on one side. I have 2 units going here. I have -3, -1, 2 here. So that becomes -2. So given such a tree, I can compute the demand across every edge highly efficiently by just doing some type of dynamic programming, depth first search, you name it. It takes order and time. And this is the cut approximating family for the tree. This evaluates you min cut and max flows for a tree exactly. Because once we have this flow, we can just go and just evaluate this quantity. So this is the amount of flow along the edge. This is the amount on the this is the capacity. So from a tree, what we can obtain is order n sized one cut approximating family that can be evaluated in order n time. This is pretty much the best we could ever hope for a graph. And the fact that this tree is within a polylog factor of the graph G also means that this is a polylog approximation. This is also a polylog factor approximation of all cuts in G. So the immediate reaction from seeing such a good cut approximation family is what happens if you use it in conjunction with Jonas' algorithm. So this is the main algorithmic idea I'm hoping to go with here, except that it has as stated, it has a big issue. So this is RST14. So what I get that alpha is O tilde 1, so polylog n. Substituting that alpha into this factor, this alpha it's just a polylog n factor. So what I get by combining these two algorithms is that I get O tilde epsilon to the -2 iterations. So that does imply a nearly linear time algorithm for approximating maximum flow. Except that there's a detail that I'm hiding here. Well, there's a very major issue that's happening, which is that what's the cost of constructing these trees? A general algorithmic phenomenon is that the better the object, the more expensive it is to construct. So Satish probably knows the literature better than me about this, but my impression is that the first algorithm by Reiki was not even polynomial time. It used one of these existential statements. And then there were results by Biankowski, Kolinovsky, and Reiki, as well as Harrison, Hildrum, and Rao, that showed how to construct these things in polynomial time. And the main idea in the construction of these routines is what they rely on is they rely on approximate sparse cut oracles. So they rely on high quality ways of partitioning a graph in a top-down manner. So the general idea of this construction is that the way they build such a tree is that they take a graph, they cut it into pieces, and they repeat. I guess since several of the authors on this sequence of works are in the audience here, you can probably ask them. They can probably give a much better description of what's happening here. There were also subsequent improvements on how to compute these partitions. There was a result by Kandekar, Rao, and Vazirani that showed that it's possible to approximate sparse cuts using approximate single commodity maximum flow. And in his talk on Monday, Reiki showed that it's possible to combine it showed an algorithm that I like to view as a combination of these ideas. Of course, there are significantly new developments in there that makes all this, that gets all the pieces to work together. That basically, if you chain these results together to show that it's possible to construct these in time that's essentially solving a set of maximum flow problems. So these can be constructed. It needs to approximate undirected maximum flow. With error, that's roughly 1 over polylog n, so 1 over log cubed n with some other constants. On graphs whose total size is roughly m polylog n.
You mean the sum of the sizes of all of the graphs that you're going to do max flow on?
Yes. So this is so what's happening in this kind of algorithm is that as we do this decomposition, because it's a recursive top-down partitioning, at every step the partitioning is done by invoking approximate maximum flow calls, actually a sequence of approximate maximum flow calls. So the total cost is actually a sum of a set of maximum flow calls. At least at the top level, the maximum flow calls, the graph is already my entire graph. So because the running times are usually additive in that if I have two problems of size A and B, running them separately is usually less expensive than running the algorithm on a problem size A plus B. I will just pretend that it's essentially running an approximate maximum flow call on a graph whose size is roughly m polylog n. So there is the issue of construction. And the way that Reiki, Xia, and Tobig constructed these trees in their algorithm is that once they invoked the Kandekar-Rao-Vazirani algorithm in a white box manner for approximating these decompositions, what they then did is they invoked the almost linear time maximum flow algorithms by Sherman as well as Kellner, Lee, Orrick, and Sidford. But on the other hand, let's consider a bit of a crazy idea, which is that let's just do this recursively. So I'm going to use this algorithm in the sense that every time I want to solve a maximum flow, I use the RST routine to compute a cut approximator, and then from this cut approximator, I'm going to use it to solve. I'm going to use the almost route routine to solve the maximum flow problem. So let's let T of m to denote the runtime on an instance of size m with epsilon equal to 1 over log cubed n. This log cubed n is just because of this error setting. I will set error to that just for simplicity. Reason it makes things simpler is because the dependency on error is just polynomial. So if my error is 1 over polylog, my overall runtime just loses a polylog factor. So what I get then is I get T of M is less or equal to T of O tilde M plus O tilde of M. This O tilde just comes from here. So I've just done 2 of the biggest no-nos when describing recursive algorithms. So the first is that I'm putting a O tilde inside the total size of the instance that I'm recursing on. This is usually problematic because I can usually hide a whole bunch of constants there. But let me assure you that for this talk, that all this notation is really just there to simplify notation. And once you plug in the explicit log factors, there is actually a way to choose parameters so that things work out.
And it's explicit in the note on archive, right?
Yes, this is explicit. Also, there's a note about this on archive, and it's explicit in that note. The second bigger problem is that if you think about this recursion, what I'm doing is that I'm recursing from a graph of size m onto a graph that's m polylog n in size. I'm recursing onto a bigger instance. And this is not something that terminates. My runtime is essentially infinite. I've just given you an infinite runtime algorithm. But on the other, and the rest of this talk, I'll just try to fix this. So to fix this, notice that there are some very good properties of this recurrence. Notice that the second term is not recursive. All the recursion is made in the first term. So, and the first term, what it corresponds to construction. While the second term corresponds to solve. And what I want to do is I want to somehow move some terms from the first term to the second term to get a recursion that does terminate. So specifically, what I want is a recurrence of the form of Tm equal to T of m over 2 plus order polylog n. This is a recursion that we're all familiar with. This recursion says every time my problem size halves, which means that at the end of the day, only the top level cost of my recursion is essentially my total algorithmic cost. So what I want to do is essentially I want to take some log factors off this term onto this term. And once I'm able to do that, I can get a fast algorithm. And the main idea is that the first term is essentially the size of a graph, while the second term only depends on the quality of the cut approximator I construct. So the plan is to use routines that trades the size of my problem instance for an approximation factor. Recall the assertion earlier that the better quality object I construct, the more expensive it is to construct it. I'm using the corollary of this, which is that if I'm willing to lose factors of approximation, I can get away with constructing things on smaller objects. And the way that we obtain these size reductions is via objects known as ultra-sparsifiers. These are tools that were central in the construction of the near linear time solvers by Spielman and Ten. I claim that their use can be traced back as far as the Klein-Karger-Tarjan linear time algorithm for computing minimum spanning trees. The general idea is that I want to reduce the size of my problem by some factor while incurring an error of approximation that's proportional to the same factor. So this is that, suppose I have a graph G, m vertices, m edges. And I can pick any parameter kappa, which is basically the error of my approximation. And what I get to is I get to H that is within a factor kappa of G. And the size requirement that I want for H is that I want H to be on the same vertex set. But I want to severely reduce the number of edges in H. Actually, it's not really severely reducing. What I want is that H is n minus 1 plus m polylog n over kappa edges. So this is so there are now a variety of constructions of these objects. One of them is in a result by that I had with Yannis and Gary. And what they come down to is they can be proven using tools such as matrix Chernoff bounds and low stretch spanning trees. Of course, you can also use because we just want to preserve all cut sizes. We can also use cut sparsifiers. So these are the Benziger-Karger algorithm for preserving all cuts in these routines as well. But on the other hand, notice that we have not really reduced the number of edges by too large of a factor. Suppose m is something like 2n. I still have n minus 1 edges. But in some sense, this is necessary. Because if I have a connected graph, I need to have a connected graph. I need to have a connected graph in order to even have connectivity, because otherwise I'm approximating a non-zero number with a 0. So the right way so we need to do another step of size reduction once we have these objects. And here the idea is that this kind of graph size, so n vertices, n minus 1 plus m polylog n over kappa edges, that should be really viewed as a tree plus m polylog n over kappa edges. So think about a graph that is a tree plus a single edge. If I have a graph that's a tree plus a single edge, and I have some demands at the leaf vertices. The leaf vertices, the demands can still just be routed. There's only one way to route those demands. They go to their parents. So once you start eliminating these leaf vertices, what you eventually get is you just get a cycle. And a cycle can also be shrunk because it's just a path. And you can also contract that into a fairly small size. So in the construction of the efficient cut approximating scheme originally due to Maudry, what he showed is that such a graph corresponds to one whose vertex and edge counts are both proportional to the number of off-tree edges. So this is due to Maudry 10. And what he showed is that this can be reduced. It gives you H prime with O tilde M over kappa vertices and edges. Furthermore, what he showed is that if I happen to have a cut approximator for H prime, I can bring it back into a cut approximator for H. That's only a constant factor off. So if R prime is alpha cut approximator, for H prime, and then there's a routine that converts such a, I should be using C prime and C. If I have a set of if I have an alpha cut approximator for H prime, I can convert it C to convert C prime, such that it just only works by a constant factor. This constant factor is in fact 2 or 3. I think it was 2. So this is our size reduction routine. The idea is that we go from G to a graph that is off by a factor of kappa. We reduce the size of that, and we build a cut approximator on the smaller. We bring the cut approximator for the smaller graph back onto the original graph. And because we have that h and g are within a factor kappa of each other, what we also have is that this is order alpha kappa for g. So then the final algorithm is just to take this kind of algorithmic framework, but introduce a size reduction when we start. This is plus ultrasparsifiers. So the general idea is that I go from G to H. I will pick this parameter kappa later on. And then from this H, I'm going to reduce it. So I have that H is within a factor. As a side, I will just track all the conditions that I have. So I have that H is within a factor of kappa of G, and then n minus 1 plus O tilde m over K edges. And then I reduce its size to get H prime. So what I have now is that H prime is just O tilde m over K, kappa total. And then I'm just going to recursively call this algorithm inside the RST algorithm for constructing cut approximators. So I'm going to get a cut approximator family for H prime. And the total cost of this is the total number of edges in H prime times a polylog factor. So my construction cost becomes T of O tilde m over kappa. Because the size of my H prime is smaller by a polylog factor. And then I can just bring this C tilde back into C using the converge routine. And what I have from the guarantees over there is that the conversion routine only loses me a factor of constant from H prime back to H. And because my H and G are within a factor kappa of each other, what I have is that C is a factor polylog n from H, and therefore is also polylog n times kappa from G. So one condition that I forgot to state is that the guarantees of the RST algorithm also gives that C prime is within a polylog n factor of H prime. So I have that. So now I have a kappa polylog n approximator for G. And then I just invoke the almost route routine. So what I'm going to finish with is to return almost route. G, C. And because the approximation factor is kappa polylog n, and the dependency is just alpha squared, what I get is that this becomes O tilde of m kappa squared. So recall that I could build these ultrasparsifiers for any kappa. What that implies is that if I pick kappa sufficiently large, all I have to do is look at this polylog factor, pick kappa to be twice of it.
Why twice?
So I can get to T of m over 2.
Oh, yeah.
So I just set kappa to be polylog n. Once I set kappa to polylog n, this kappa squared is also a polylog n factor. So the trailing term is still m polylog n. And I get a runtime recurrence that is basically Tm equal to T of m over 2 plus m polylog n. And running this recursion leads to a nearly linear time algorithm for approximating maximum flows. So that basically gives a recursive routine for combining cut approximators and for combining cut approximator with routines that use them, as well as their recursive constructions. It gives nearly linear time algorithms for approximate maximum flow, as well as constructing these hierarchical cut approximators. To me, it seems that this algorithm seems to bring up a lot more questions than it's answering, because it seems to speak, because it kind of breaks away from the way that we have been approaching approximate maximum flow problems to date. So a lot of the recent efficient routines for approximating maximum flows, they go through electrical flows, or they go through ideas based on ways of approaching electrical flow problems, so linear system solvers. In fact, the cut approximating routines in Module 10 can essentially be modified to give you linear system solvers. These cut approximating trees, there were some. I talked with Yannis a little bit about this week, and he has done some work, previous work and ongoing work on using these to build approximators build preconditioners for linear systems in graph Laplacians. And in those cases, you can actually show that these objects are very unlikely for graph Laplacians. For some reasonable definitions of trees, you can show that for graph Laplacians, there does not exist trees that approximates in the L2 sense up to polylog factors. So to me, this seems to give an algorithm that actually uses special properties of approximate max flows, and also the L1 and L infinity notion of congestion, and takes advantage of the fact that there are stronger objects in the L1 sense. Seems to suggest that there are reasons to believe that approximate maximum flow and also problems in L1 can have additional properties than L2 problems, and might actually be easier than some of these L2 problems. Certainly, it also suggests that combining some of these ideas with ideas from L2 algorithms may lead to further gains. That's all I have. Any questions?
That the best algorithm we have for max flow is better than the best algorithm that we know of for like L4 flow or something like that.
So the question is about L4 flow. So there's one way to view the maximum flow problem as an L infinity flow. This is that I want to minimize the L infinity of my flow vector subject to demands. This view is kind of nice in that it allows me to also couch electrical flows as L2 flow problem. So the question was about, what about L4 flow problem, which is between L2.
Between 2 and infinity.
Yeah, so my impression is that you have some routine for doing, say, L4 flow using the Module framework.
Right, and you could use, I think, either the Sherman algorithm using that framework or the Kellner-Lee or Recursive. But since we don't have those trees, it doesn't seem like this works, which is interesting. Because it seems like it means that problem expecting between L2 and L infinity, we can't do as well as we can do for either of those two extremes at the moment.
So I guess that's another question onto the list, added to my list of things I don't understand about the implication of this. Yeah, I'd love to hear more about, do you know if there are ways to convert these schemes into ones that preserve, say, L4?
It doesn't seem like it, because if you can't do L2...
Right.
What is so you can do oblivious routing in LT norm.
Oh, right.
But that's using a union of a bunch of trees, not with one tree.
This does not work by one tree.
Right.
That's an interesting question. And I don't have a very clear answer to it. I'm sure in a year we'll have a better answer to that.
So I guess a point to be made about the quality of these single trees as preconditioners is that the worst case is the path graph, when the preconditioner is the binary tree. But there's more general classes of graphs. General classes of graphs, for example, 3D grids, for which one single tree will give you a condition number which is about third root of n, which is much better than what you get with a single tree or spanning tree. And
So you're saying standard trees are much better?
yeah, for large classes of graphs. Right? I guess for expanders they are perfect, right? So it's like a constant approximation. So for graphs that are between the path, which is the worst case, and the expander, there are better condition numbers that you get from them. And maybe that explains partially the reason the solver is behaving without practice.
So you think the runtime of the standard tree preconditioners are actually something related to, say, the 1/3 power square rooted?
In 3D grids, but it depends. For example, in more expander-like graphs, that will be even better. Small, assuming you can find these compositions required for that.
So this is a very interesting connection because in L2 there are a bunch of ways of combining, of analyzing these things that look very similar but gives you very different bounds than when we do them with L infinity. And this is also one of the things that I think that's worth exploring based on these.
Okay, well, thank you very much.